Our next speaker is Matthew Dack from CGG. He joined as a geoscientist working in the multi-client and new ventures region in 2013. He has a degree in geology from University of Liverpool, and subsequently petroleum geoscience at the University of Manchester. He's worked on data sets from a number of regions in the UKCS to West Africa, particular focus on CGG's comprehensive coverage of the UKCS. And I think, it's quite long. I think at that point I'll hand it over to you, Matthew. And
thanks, Jim. Morning, everyone. Today I'm going to be taking you through the integrated geoscience and the latest processing techniques that CGG has been using to maximise the value of its UKCS datasets. I'll take you through a bit of a background through CGG's coverage in the UKCS in relation to the 30th round blocks. I'll then take you into a bit of background about the lodestone survey itself, take you into the bones of the integrated geoscience, and then show you some of the results from the uplift that we've achieved. So with the background, here we have CGG's data coverage on the UKCS. On the right-hand side, we can see the coverage provided by the TerraCube datasets. And on the left-hand side here, we have our 3D long offset datasets, including the Judd 3D, Runestone, Cornerstone, and Lodestone, which cover much areas, including the west of Shetland, North Viking Graben, Central Graben, and the southern North Sea. In addition to this, we also have some broad size and dual azimuth datasets that cover parts of the North Viking Graben and the central North Sea. But today I'm going to be focusing on Lodestone, the southern North Sea dataset. So here's Lodestone. It was initially acquired in 2010 to 2013 in 3 phases and initially processed to PSTM. In 2014-15, CGG undertook a depth processing program, and the survey covers prospective areas of the Permo-Carboniferous in the southern North Sea. Here's some highlights of the acquisition and processing. Key things to note are, due to the shallow water, it's conventional flat tow, and then this has been processed with a number of techniques. In particular, we had focus on the demultiple, trying to improve signal to noise in the Permo-Carboniferous, and we've also applied deghosting and 6 passes of multi-layered tomography. Just to touch on briefly the geology of the basin as a whole, with the strat column and the play cross-section. Sorry, it's a bit blurry, but the regional geology consists of a regional Westphalian coal measure source, Permo-Carboniferous sands, and the regional Zechstein salt seal. Although the basin is considered mature, there's still new opportunities to be had, signified by the recent Cygnus development. So here we have an example of the original PSTM, and now we can see the uplift that's been achieved with the new PSDM data. Key features to note are we can see the thick Zechstein salt package, the Permo-Carboniferous target underneath, and here we have the Cygnus discovery. If we take a zoom in on the Cygnus discovery, we can look at this working petroleum system. We have the Carboniferous play fairway with intracarboniferous sands and interformational seals, trapped in rollovers and anticlines, and sealed by interformational seals. This is separated from the Rotliegend play fairway by the well-illuminated base Permian unconformity, where the reservoir is the Le Mans sandstone, trapped in tilted fault blocks and sealed by the thick Zechstein salt. So now we'll get into the bones of the depth processing program and the different techniques that were used. So here again, we have that PSTM dip line. And now we can overlay the 3D structural interpretation that was carried forward for the velocity modelling. In total, 11 horizons were picked to mark key velocity boundaries, and not all of these were taken through to the model building process. These time horizons were then depth migrated using a number of different depth migration techniques in order to assess the variability of simply depth migrating time horizons as opposed to the seismic itself. The key methods that were used were a simple average velocity to base Zechstein, interval velocity map layer cake method using the well data, and also a V0K method where the interval velocities from the wells was used to derive V0 values and K values. And here we can see the results of these depth converted horizons on the final PSDM volume. We can see The V0K method works fairly well in the shallow, but as we get to the deep, it's failing to account for the lateral thickness and velocity variations. When we overlay the layer cake model, we see it's fairly close to that of the V0K, but the average velocity method is too simple in a complex salt basin such as this. But in all, this signifies the importance of depth migrating the data rather than just your horizons when trying to assess the subsalt prospectivity in this area. And this is exemplified here. We can see we have a map of the base sextine top rock Liegend in time, and we can compare this to depth. And we can see the different structuration of this horizon resulting from the different velocities of the overburden. So again, when we're trying to identify prospects below the salt, it's crucial to be looking at the data in depth. One of the aspects of integration we used when processing the data was the integration of our multi-physics team, and in particular gravity data. The power of the gravity data is clear to be seen when we take a look at, firstly, the top sextine structure and isopac, and then the Bouguer gravity. When we overlay the structural contours, we can see that there's a very good correlation between the gravity and the salt structure. And therefore, this became a powerful tool when trying to assess the structural interpretation in areas where the time imaging falls short. And we have an example of this here. We have a east-west line across a north-south orientated salt wall. And we can see here we would struggle to interpret the geometry of this salt feature, in particular the flanks. We could hazard a guess of something like this. It's made even worse when we take a look at a strike line down that salt wall feature. We can see the complex nature of the salt, and trying to accurately interpret the top and base salt here would be very difficult. We could hazard a guess of something like this, but again, it's tough. So therefore, the gravity became a powerful tool in trying to aid our interpretation where the seismic imaging falls short. One thing we were able to do was conduct gravity modeling. To do this, we were able to convert our background velocity model into a density model using the Gardner's relationship. And then when we combine this with our 3D structural interpretation, we were able to calculate the expected gravity response and compare this to what we see in the Bouguer gravity. We have an example here of that workflow in action. Again, we have the background seismic volume here with a crude salt interpretation. When we add in our background density volume, which again is calculated from the velocity model, note the fact that we have a constant density for the salt because in the early model stages we had a constant velocity for the salts. We get a calculated gravity in red, and we can see that this differs from the observed Bouguer gravity. In order to try and refine the model and make the lines a curve, lines make the curves align. We can then try things such as increasing the density of the salt, which we've done here, and we can see that we get better alignment between the observed and the calculated gravity. To take it further, we can alter the structural interpretation. Here we've made the salt thinner, we've added an overhang in the salt wall, and now we can see that we're getting very good alignment between the observed and the calculated gravity. So we've gone from an initial model of this to a model of this. Now in areas of poor illumination, such as around the salt wall, there's good rationale for adding an overhang here. We can't accurately determine the geometry, so it's worth testing. However, in the adjacent areas where the seismic imaging is good, we can assume that the seismic resolution is greater than that of the gravity, so there's no rationale here to change the structural interpretation. So this points towards something else going on. Perhaps maybe the velocity is not being calculated correctly within the salt. It might point to the fact that using a constant velocity for the salt isn't viable here. To take it further, we could look at the areal extent of the gravity anomalies. So here we can see where the calculated and observed gravities differ spatially across the lodestone survey. When we invert the upper sextine densities, we can see distinct regions, northwest, southeast regions, where higher density material would be required to make the curves align. So we could then look at these details in a bit more area to try and work out what's going on. Here, again, we've got that same inverted density map, and when we compare it to the top salt structure map, again, we see that there's a good correlation here, and we see that this anomaly seems to be confined to an area of salt withdrawal. If we take a look at that in cross-section, we can see we have this area of thinner salt with a number of high-amplitude events within it. When we take a look at the literature in the worlds, we know that the Zechstein has a classic cyclical fasces variation of shale, carbonate and hydrite, halite. And so we can take this forward into our thinking. When we take a dip line across the feature, it's even more obvious, this withdrawal syncline. And again, we see these high amplitude events. Therefore, we're able to evoke a model where sediment loading has resulted in salt withdrawal here. Due to the fact that halite is more mobile than anhydrite, it's preferentially squeezed into the adjacent pillows, leaving behind an area of thin salt with high velocity anhydrite in it, creating a fast zone, which may have been underestimated in the velocity model building. We see this again when we take a look at the RMS amplitudes across the feature. We can see that there's relatively higher RMS amplitudes within the Zechstein withdrawal feature as opposed to the adjacent areas. So again, this is something that we can then consider in the velocity model building and start thinking about perhaps there being merit to using a salt thickness formula when we're doing our processing. There are also more anomalous features. These are created by tertiary dikes, which we were able to identify. And these are easy to identify. They create linear crater chains in the top chalk horizon. And these also had to be accounted for in the velocity model building. Now that we've taken a look at some of the processes that we went through in the processing sequence, we can now look at some of the uplift in the results. So here we have an example of the uplift from the salt modeling. We have before salt modeling and after salt modeling. And we can see the improvements that we're getting as a result of changing the salt interpretation and velocities. We're getting much better illumination of the base Zechstein reflector. It's generally flatter, more continuous, and we're getting less pull-downs and push-ups created by the overlying salts. That was for one area of the salt wall. However, if we take a similar strike line to the one we looked at earlier, the uplift is even better to be seen here. Again, going from before modeling to after, we can see that we're getting a much more continuous, better illuminated base Zechstein reflector, and we're getting less of those pull-ups and pushdowns created by the complex overburden. As I mentioned earlier, one of the key things which we wanted to focus on was the removal of multiples from the target area. And one way in which we did this was with the use of targeted multiple attenuation, where multiples associated to specific generators were removed from the target area. The three generators used were the top Speeton, the Speeton to Bunter package, and the shifted top Zechstein reflectors. And here we have an example before the demultiple and after. Now, the key thing to note here is the fact that we're able to remove some of that low-frequency multiple, which is clouding the target interval. And these are the targets for exploration, so it's key to try and remove some of that noise. So going back to the line I showed earlier, we've been able to take the data, process it in depth, and improve it to this. With the help of the demultiple workflows, we've improved signal to noise in the Permocarboniferous. In addition to that, we've got much better illumination and continuity of both the crucial base Zechstein horizons and the BPU. And with the deghosting, we now have better shallow and deep imaging alike coming from the additional bandwidth. And then finally, with the accurate velocity modeling, we're now getting reliable structures in depth and a much better weld to seismic tie, which we can see here from the mist tie analysis for the base Zechstein reflector. We can see incremental improvement in the average mist tie from the wells until we get a final mist tie of around 19 meters, which, considering the subsalt location and depth, is fairly good. And these are the reliable structures in depth that we're trying to identify, which are the targets for exploration. We see a number of rollovers and anticlines. For all of the previous comparisons to compare the original time data with depth, we've been using a depth stretch to time volume. But to show the impact of the time versus depth comparison, we can compare the time data with the depth, and we can see the change in structuration to that pre-Zechstein section, and in particular the base Zechstein horizon. And again, this is crucial when we're trying to identify prospects within the subsalt to have accurate depth imaging. The quality of the data is such that we've been able to do some additional work. This project focused on the Paleozoic faults. We were able to do some automated fault extraction using CGG's Insight Earth software. And here we have a rose diagram showing the dip azimuth of all of the Paleozoic faults. And we see that this corresponds well to the structural interpretation of the base Zechstein. And we can see these faults both in 2D and 3D, and they populate heavily the Cygnus area, so they form critical structural components to many of the discoveries in the region. So to conclude, showing some of the areas up for offer in the 30th round, we have here the final depth image of the base sextine reflector across blocks 44, 7 to 10. And now with the new data, we have these structures reliably in depth. In addition, with the improved signal to noise and with some of the fault extraction workflow, we've been able to identify even the most subtle Paleozoic faults, which might form crucial trapping components. With the improved signal to noise in the deep section and the removal of side lobe energy, we now have much more reliable amplitude information for AVO and inversion work. Within the data set, there are two of the unsanctioned discoveries. To save time, I won't go through them massively. We have the Clark prospect, which we can see here, and we also have the Lauren prospect. If you want to view these in a bit more detail, please come and see us. So to conclude, CGG has extensive data coverage over the UKCS, in particular the blocks on offer in the 30th round. The Lodestone survey, covering approximately 4,000 square kilometres of Quad 44, provides long offset 3D data in depth. With the Lodestone 3D survey, CGG has shown that with integrated geoscience and the latest processing techniques, including accurate velocity modelling, particularly of the salt, we now have proper depth imaging, and it's maximised the value of our southern North Sea dataset. The resulting PSDM helps to illuminate those pre-sextine permocarboniferous plays and prospects that we're trying to identify. If you have any other further inquiries, please come and see us on our booth. Thank you very much for listening.
Thank you very much, Matthew. Questions? No questions. Okay, and then I'll have just one quick one. Obviously, depth key, velocity model is key. We've been hearing a lot about FWI today. Do you have thoughts of trying that?
I don't think it was used in this depth processing program, but certainly, particularly as we've seen in some of the other areas, the shallow channels can cause problems when it comes to building the velocity models. And if you can accurately solve the shallow, then you're going to help ultimately with the deep. But it's certainly something that could be added to this survey.
Okay. All right. Well, if there's no questions, thank you very much. Very interesting talk. Thank you, Matthew.